Hi, I'm Paul Morin with the Energy Conservatory, and welcome to our webinar titled Measuring Air Handler Flow Accurately. So our agenda today, we'll be covering why measuring air handler flow is important, advantages of using our TrueFlow air handler flow meter. We'll talk about the system components, what's included in that, what gauge options you have. You're certainly not required to use a DG700. Using other gauges may affect accuracy, and we'll go over that. Basic TrueFlow test procedures. Procedures with 2 returns. So we get those phone calls fairly often. Those are fairly common in different parts of the country. So if you've got a 2 return system, what are your options for measuring airflow in that type of situation? And then we'll talk about using the Duct Blaster. The Duct Blaster can be used to measure air handler flow, and we'll talk about using that method. If you already have a Duct Blaster fan, you can use it to measure the total air handler flow, not just the duct leakage. And then we'll talk about troubleshooting airflow problems. So if you measure the airflow and it's an issue and you're not sure what the next step is, we'll talk about troubleshooting some of those flow problems that you might have with your air handler system. So why is measuring airflow important? Insufficient airflow is certainly a common problem that we see. And low airflow can lead to decreased capacity, certainly decreased capacity if you're not getting the proper airflow. You could even be freezing up a coil if not enough air is moving across it. You'll see increased energy usage and certainly comfort problems if the air conditioning or heat isn't being distributed to where it's supposed to be properly. And also being able to accurately measure airflow will allow you to optimize performance of your heat pump and air conditioner. You need to know what the airflow is. You need to set the airflow accurately before you set the charge on the system. So when you're setting up a new system, you need to accurately know what the airflow is. So some advantages to using the TrueFlow is some of the widely used methods are problematic or time consuming. You want a method that's simple or accurate. Certainly having a quick, easy way to give you the accurate results you're looking for is very helpful. And it's proven success over years of field testing. It came out in 2001, and it's widely used throughout the HVAC and home performance industries. It can be used with any manometer with a resolution of 1 Pascal. Those of you that are using inches of water, it's 0.005 inches of water. The DG700 has a resolution of 1/10 of a Pascal, but you can use a pressure gauge with a resolution of at least 1 Pascal. Flow accuracies, plus or minus 7% when you're using a gauge that has a 1% accuracy. Or if you're using the magnehelic gauge, you'll have about plus or minus 9% accuracy. The flow range, the number 14 TrueFlow plate, which is the size of it's 14 by 20. You can measure airflow 365 to 1565 CFM. And the larger plate, the 20 by 20, the number 20 TrueFlow plate, 485 to 2100 CFM. System weight is going to be about 13 pounds for the total system. So the components include the carrying case pictured at the right. Everything neatly fits into that carrying case, and it folds in half and zips up and has that carrying handle to move it around. It includes some laminated flow conversion tables if you're not using the pressure and flow gauge. It has a 10-foot blue and a 30-foot clear tubing, and an operations manual, along with the 2 calibrated plates, the 14 by 20, the number 14, and the 20 by 20, number 20 true flow plates. Comes with both of those, along with 8 spacers for sizing adjustments, and so it will include the most common, it'll fit the most common filter sizes. Also includes a static pressure probe that's got a magnetic connection to attach to the side of a plenum. And gauge options, again, gauge resolution of 1 Pascal or 0.005 inches of water, which would be a DG700, DG500, DG3, or DG2. Other digital manometers, there's a lot of other manometers out there that would meet this resolution of 1 Pascal requirement, or a magnehelic gauge. So the basic procedures, you want to get the most accurate reading, you want to be at the location closest to the air handler. So if there's a filter grill right at the air handler, that's a preferred location to, say, a return filter grill, if you have the option of the 2. The basic test procedure, with the air handler on and the filter in place, will measure the normal system operating pressure, and you'll see that abbreviation NSOP a lot throughout this presentation. That's the normal system operating pressure. And we'll replace the filter with the true flow, and then we'll measure the true flow system operating pressure, which is likely to be different than the normal system operating pressure. The filter may be more restrictive, or the true flow may be more restrictive, but they're likely to be a different number. And if the pressure is the same, the flow is the same, so we need to make an adjustment. Then we'll measure the airflow next, is the next step, and then calculate the flow resistance correction factor. We can use either a chart or a formula to come up with that correction factor, and then we'll use that correction factor to calculate the adjusted flow. So our setup, first, if we've got a dirty filter in there, it's a good idea to replace it with a clean one before taking our normal system operating pressure. We'll want to make sure all the registers are open, so we'll get the maximum flow through the system. We'll want to open a window. If when we turn on the air handler, it changes the pressure in the room, that's a problem, because we're reading the operating system pressure with respect to the room we're in, and if the pressure in the room changes, then we're getting the wrong number. So we want to open a window to the outside. If our air handler is in a crawl space or an attic or a garage, we'll want to open that space to the outdoors. So turning on the air handler won't affect that pressure. Then we'll insert our static pressure probe, and we'll want that probe to be pointing into the airflow. We can install it on the side of a supply plenum, and by the side I mean if you're facing an upright air handler and there's a trunk coming towards you and a trunk going away from you, you'll want to install the static pressure probe on the side of the plenum, on either the left side or right side of the plenum, the sides that don't have the trunk lines coming off of them. You could put it in the dead end corner of a supply plenum. That's going to be a location also that's going to have a pretty stable static. And a dead end corner is defined as a corner that doesn't have duct or a trunk line or a register within 8 inches. So if none of those 3 things, a duct, a trunk, or a register are within 8 inches, then we'll have a pretty stable pressure there. We could put it on the side of a return plenum if that return plenum doesn't have a trunk line, a return register, or a return duct connected to it. We want that static pressure probe to be at least 24 inches from the true flow plate, 24 inches from a 90-degree corner, and 24 inches from any return trunk line connections. And also, if we're installing our true flow plate at a remote filter location, then we don't want the static pressure probe going in the return plenum. Next, we'll enter the normal system operating pressure if we're using a DG700. And using a DG700 simplifies this process because instead of recording the normal system operating pressure and the true flow system operating pressure and using a chart or a formula to determine the flow resistance correction factor, it's all done internally. So you can simply enter the normal system operating pressure into the DG700, similar to entering a baseline into the DG700. So those of you who do blower dart test are familiar with that baseline function of the gauge. So you'll enter in that normal system operating pressure, and then the DG700 will automatically adjust the flow for the difference between the normal system operating pressure and the true flow system operating pressure. So it really makes that whole process much simpler. So we'll connect the tubing from the probe to the gauge. We will turn on the air handler, set the DG700 to the pressure air handler mode. So we'll click our mode button on the DG700, and we'll push it, keep pressing it until we toggle across pressure flow at 25, pressure flow at 50, etc., until we get to the PRAH mode. When we get to the PRAH mode, we're going to see NSOP flashing. Once that begins flashing, we will push the start button. So start button is in the middle here. Once we push start, we'll see the seconds start to count off. So these are seconds, and it'll count off 1, 2, 3, 4, 5. And once the pressure on the left becomes stable, this is going to display a long-term averaging. So over time, it'll get more and more stable. And once it stays the same for 3 or 4 seconds, we can push enter, and then that enters the normal system operating pressure into the gauge. Next, we'll install the true flow plate, and as you can see, you can install that at a remote filter grill. If you've got a filter grill right at the air handler, either horizontal or vertical, you can install it there. And if you have one like is pictured at the right here, where you have a return drop, you want to make sure that the spacers are on the top, because as air is coming down that drop, there's going to be a lot of airflow at the bottom, and if you have that spacer at the bottom, you'll miss that. Some of that. You'll be adding resistance to that airflow where it really doesn't need to be. So you'll remove the existing filter, choose the appropriate true flow plate. You'll add the spacers top and side as needed, and you want to face the front into the airflow. And the front is defined as the side that has the two diamond-shaped Energy Conservatory stickers on it. You want that to point into the airflow. It's important that all the airflow must pass through the plates and not around the plates. And all the air must also pass over the plate. So if you have a 14 by 14 register that you want to put the true flow plate over, and the true flow plate is 14 by 20, all of those holes don't have air passing through them. It's measuring total pressure and static pressure and averaging them over the array. And air must pass over that entire plate, not just part of it. Otherwise, it'll be averaging. It'll be including averages from locations where there's no hole, where the holes aren't seeing any airflow. You want no obstruction 6 inches upstream or 2 inches downstream. That can affect the accuracy. So the air handler's downstream. If that's less than 2 inches away, that could be problematic. So 6 inches upstream, 2 inches downstream. It can be installed right inside the air handler cabinet. You can tape it in place or wedge it in place as long as no airflow is going around it and all the airflow is going through it. You could install it inside the air handler cabinet, as long as you have at least a 2-inch space between the TrueFlow and the air handler fan itself. Next step, we'll measure the adjusted total flow. So we've installed the TrueFlow plate. We've already taken the normal system operating pressure and entered it in the gauge. We'll connect the 2 tubes from the TrueFlow plate to channel B. There are colored tubing on that, but where you connect the tubing, you'll get the same measurement whether you put a tube on input or reference. So you'll connect those 2 tubes, one to input, one to reference, the 2 tubes coming from the TrueFlow plate. We'll change the device to TF for TrueFlow. So we'll push the device button on the DG700 gauge, and we'll keep pushing that to toggle across the different devices till we get to TrueFlow. And then we'll change our configuration to match the plate being used. The default will be 14, and if we're using the 20, we'll hit the config button and toggle to 20. Next, we'll turn on the air handler. If our numbers are fluctuating, so if our flow numbers on this side showing 1566, if those numbers are fluctuating, we'll click the time average button and we'll toggle through from 1 to 5 to 10 to long. And we'll leave it at long-term average until our flow number is pretty stable. And once that stays the same for a few seconds, we can either push hold or we can write down that number. Either way, we'll need to write it down because the DG700 doesn't store numbers. So we'll record our adjusted flow reading. And the reading that's being displayed, you see it says ADJ here. And that means it's making the adjustment for the difference between normal system operating pressure and TrueFlow system operating pressure. It's automatically making those adjustments. You don't need to look on the charts or figure that adjustment factor. It's doing it automatically. And the flow you're reading is the adjusted flow. Next, we'll talk about the TrueFlow procedure using other pressure gauges. And it's basically the same as with using the DG700, except you'll need to convert the pressure reading you get at the TrueFlow plate. So that's on channel B is where you'll have the TrueFlow plate. So you'll be reading a pressure from the two tubings from the TrueFlow, and you use that to on a chart to convert pressure to flow. And then you'll also need to adjust the flow based on the pressure difference between the normal system operating pressure and the TrueFlow system operating pressure using a chart or a formula. So to use the charts, what I'm showing here is Appendix A of the TrueFlow manual, and it has 2 different charts, one using pascals and one using inches of water. So for example, with the Pascal chart, the plate pressure, the pressure we're measuring on the gauge, will go across to whichever column. If we're using the 14 or we're using the 20, we'll move over to that column to see what the CFM is. So if we've got 68, we'll have 948 with the number 14 plate and 1279 with the number 20 plate. So that's how we convert pressure to flow using the charts. Next, we'll need to adjust the flow based on the difference between the normal system operating pressure and TrueFlow system operating pressure. So we'll record the normal system pressure, we'll record the TrueFlow system pressure. We use a chart to determine the multiplier. So this is the Pascal chart. So let's say to start with, our normal system operating pressure is 50 pascals. We'll follow that down to what our TrueFlow system operating pressure is in Pascal. So let's say it's 46. That was our TrueFlow. We'll follow that across to 50 with our normal system operating pressure, and we'll see we're at 1.04. So we'll multiply our airflow reading times 1.04 to get our adjusted flow. And the same with the, this is the inch of water chart. We'll do the same thing with normal system operating pressure and follow that down to our true flow, and at the intersection is our multiplier. So procedure using two returns. If the returns share a trunk, we can measure right at the air handler inside the cabinet if possible, or if there's a filter rack there, we can measure it at that location. The true flow plate can be put at an angle in a filter grill, or in a return drop, or a filter grill. It can be put at an angle as long as it's not 2 inches away from an obstruction downstream or 6 inches upstream. We can put it in at an angle. Sometimes returns will enter a cabinet from different sides, and if the second return is smaller than 14 by 20, you can use a transition. For example, if you commonly run across something like a second return that's a 14 by 14, you can fabricate a 14 by 14 to 14 by 20 transition, and then put the 14 by 20 plate at the end of that transition. And that way, all the airflow is moving across that true flow, and you can get a measurement on that second return that way. If you're using the DG700, it's helpful to have a long tube for the channel A operating pressure that will reach both of the locations where you're taking measurements from. And that way you can use that function where you enter the normal system operating pressure into the system, and you can use one gauge and take your flow readings separately and add them together. You know, the adjusted flow from the first grill and the adjusted flow from the second grill, and add those together. Next, we'll talk about a density correction. There are charts that you can use to correct for density, both for temperature, for airflow, different temperatures of airflow moving through the plate, and also at different elevations. So for example, if you're measuring the flow with the air conditioning running, maybe you're at an extreme at 40 degrees, and you'll see that you'll need to, at 40 degrees, you'll need to multiply it by 0.973 and to get your actual airflow number there. So it's about a 3% difference, so not a huge difference, but it'll affect your flow readings. And let's say we're at 70 degrees and 7,000 feet of elevation. Now we're up to about a 14% difference. So to multiply it by 1.14 to get our actual volumetric flow. And here's some volumetric flow recommendations. If you're in a humid climate, humid air can take on more energy than dry air, so you need less airflow. So between 350 and 400 CFM per ton. If you're in humid climates, if you're in dry climates, you're going to need more airflow, somewhere between 400 and 425 per ton. And if you're at 7,000 feet of elevation, you're going to need about 450 CFM per ton. And that's if you've made that adjustment for volumetric flow. Sometimes you'll be comparing with standard CFM, SCFM, which is converting your flow to what it would be if you were at sea level and 68 degrees in sea level. So if that's the method you're using, then if you're at 7,000 feet and 70 degrees, you'll need to multiply your number by 0.877 from the indicated flow. And indicated flow is the flow being read on the gauge. So the flow that's being read on the gauge, you'll need to multiply it by 0.877 to get it back to sea level. Then you can use that 400 CFM per ton, for example. Next, we'll be talking about measuring total system airflow using the pressure matching method in the Duct Blaster fan. And the procedure, you'll want to measure, first measure the normal system operating pressure. You'll want to connect the Duct Blaster fan to the duct system. And you want all the return airflow to be flowing through the Duct Blaster. So if you're attaching it right at the air handler, you're going to need to block off the return side. So all of the airflow that you're measuring needs to be going through the Duct Blaster fan. And then we'll turn on the Duct Blaster fan to match the normal system operating pressure, and then measure the flow through the Duct Blaster. So like with the True Flow, we will first replace the dirty filters. We'll open all of the registers. We'll open a window because if the Duct Blaster or if the air handler fan changes the pressure in the room, we won't get an accurate reading because we're reading operating pressure with reference to the room. If we change the room pressure with the air handler running, we're not going to get an accurate reading. We'll open the air handler zone to the outside. If we're in a crawl space or we're in an attic or we're in a garage, we'll want to open that space to the outdoors. And so our setup again, we'll insert the static pressure probe pointing into the airflow. We want to put that on one of the options is to put it on the side of the supply plenum. And side is defined as if you've got for example, an upright air handler and the supply trunk is coming towards you and another one going away from you. You want to insert it on either the left or right side of that supply plenum. So a side where the plenum is not connected. You can put it in a dead end corner of the supply plenum. That's a good place to measure a stable static pressure. And the dead end corner is defined as a corner of the plenum that doesn't have a duct or a trunk or a register within 8 inches of it. You can put it at that location. You can put it at the side of a return plenum without a trunk line return or register duct connected directly to it. You want that static pressure probe to be at least 24 inches from the true flow plate, 24 inches from 90-degree corners, and 24 inches from a return trunk line connections. So measure the normal system operating pressure, turn on the air handler, turn on the gauge and write down the normal system operating pressure. Then the next step, after we've recorded that normal system operating pressure with the filter in place, we will connect the Duct Blaster fan to the system. And in the middle picture, we see we're connecting that fan right directly to the air handler cabinet we'll connect the fan to a piece of cardboard and then tape a piece of cardboard over that door opening. If there's restrictions close to where the fan is there, we'll want to build it out like we're showing in that the first image here. But a lot of times those air handler cabinets are getting more and more crowded over time, where the fan is almost right against the door, and there may be some electrical connections or a board or switches or something, dip switches right in the front there that are creating a restriction too. So if we build that out a bit, there'll be less restrictions close to the fan, and we'll get a lot more airflow through the fan. So that can be a time-consuming part of using this method. But if you've already got this piece of equipment, you'll get really accurate flows using it. Or you can connect it at a remote return filter grill. So then after we've measured our normal system operating pressure and attached our fan to the system, we'll want to match the normal system operating pressure using the Duct Blaster fan. So we'll connect the tubing from the DG700 to the fan, the channel B input on the DG700 connected to the tap of the Duct Blaster fan, and we'll set the DG700 to the pressure flow mode, pushing the mode button once. We'll turn on the air handler, and then we'll turn up the Duct Blaster fan to match the normal system operating pressure, and then record the total system air handler flow. And if we have systems with low flow, if we've got a 10.5 system, for example, we might have to put a flow ring on the Duct Blaster fan. You might see that the normal system operating pressure is actually higher with the Duct Blaster fan installed than it was before, and in that case, you'll have to add ring 1. If you're not able to match the normal system operating pressure, so maybe you've got a 5-ton system, because you're starting out before you start turning the Duct Blaster fan on, you've already got the air handler running and it's drawing air through the fan. You'll actually get a flow reading on your DG700 before you even turn up the speed controller. So it's got a negative back pressure on it. So it's pulling air through the fan, and you, in some cases, you may be able to get up to 2000 CFM through that fan. So you may be able to match the normal system operating pressure. So you turn the duct, if you're not able to match the normal system operating pressure with the Duct Blaster fan turned all the way up, you want to record the CFM with the fan turned up all the way, and record the operating pressure you were able to achieve, and then use the flow resistance correction factor from Appendix B of the True Flow Manual to correct that flow based on the operating pressure you were able to achieve. So this is, if you have a Duct Blaster and not a True Flow, you can go on our website and download that True Flow Manual is a free download, so you can get at this Appendix B for the flow resistance correction factors. And so let's say that your normal system operating pressure was 50, and you've got the Duct Blaster cranked all the way up. You're only able to get it to 40. You'll follow 40 across to 50 and find your correction factor of 1.12, and you'll use that for your correction factor.
So now we've covered methods of measuring your air handler flow accurately. And what if your numbers come up to be insufficient? You don't have enough airflow, total airflow going through your system. So what are some options? How do you figure out what the issues might be that need correction? To start out with, we'll just take a look and listen for some obvious things. It might be that your supply or return ductwork is too small. There are rules of thumb, whether you're using round or rectangular duct, on the size the duct should be, depending on how much your required airflow is. So you'll have to calculate based on your BTUs of heat or your tons of air conditioning, how much airflow you need. And once you've done that, then you can calculate what size duct you're going to need at a minimum for delivering the airflow that you need without adding too much restriction. And you know, it may be that you know, you can see some pretty obvious things. One of the common things you might see is that a return air duct coming up through going through a crawl space and coming up through a 2x4 cavity. So now you've restricted that that duct. Maybe it's two stud cavities wide, and it's tall enough, but you know, where your central return filter is, maybe that's big enough, but it's only 3.5 inches deep. So that really is a restriction, and you may be seeing 100 pascals or more of resistance because of the airflow going through such a small cavity, and it might need to be enlarged, up to 8 or 10 or even 12 inches deep in order to get enough airflow through that center return. Oil canning or oil panning, or there's a few different terms for that sound that you hear when the air handler comes on. You hear a banging sound because either the return is getting sucked in or the supply is getting pushed out as soon as the air handler comes on. So clearly, if it's doing that, if it's enough to move the ductwork to make that kind of a noise when the air handler first turns on, then you've got some issues with restricted ductwork. Whistling is certainly an issue. You've got too much velocity trying to get through a small register, and you can hear the noisy sounds, and that's a pretty good indication that your ductwork is too small also. So looking and listening for some obvious problems. Some other obvious things, closed dampers. If they're trying to push air to a room over tuck under garage, maybe there's some bedrooms over a garage that are the farthest away from the furnace, and maybe you're not getting enough airflow there, so you're choking off all of the other dampers to try to force air out over that space that's not heating or cooling properly, and that may be causing enough of a restriction where you're getting high static pressure and low airflow. Dirty or restrictive air filters are certainly an issue where check and make sure they're clean, and if you've got some pleated filters, sometimes they're just too restrictive for the amount of airflow. So some pretty obvious things. Maybe you've got flex duct that isn't pulled tight. There's been plenty of documentation and studies that show if the flex duct is pulled tight, or if there's rigid elbows when you're using flex duct, you can get pretty good airflow through it. But if it's sagging or making turns, then you run into issues with not enough airflow through flex duct. Dirty fan blades, certainly over time, they get caked up with dust, and they just can't move enough airflow. So sometimes you have to pull that wheel, pull a motor, and take those into a wash tubs or power wash them or something to get those, scrub them, get those fan blades cleaned off. It's amazing what you'll find when you look. Wrong speed settings on the fan, certainly increasing those fan speeds will help. You want to, whenever you do that, you want to check static pressure, and we'll be going over that a little bit later. But try upping the fan speed to get more airflow, and that may be a solution as long as your static pressures aren't getting too high, because that's going to be hard on your motor, the longevity of your motor, if your static pressures are too high. Maybe a dirty or frozen air conditioning coil. That can certainly be an issue, and we'll talk about what, if you measure the pressure across the coil, what numbers are good numbers, and what numbers are bad numbers. And then, so the next step really is to confirm these things. Some of these things are pretty obvious, and but there are ways where you can take pressure measurements to confirm what you suspect. So, we're gonna hypothesize based on what we're seeing, but then it's always a good idea to take some measurements. You've got the tools, you've got a good pressure gauge, static pressure probe, and you can take some of those measurements to confirm what your theories are. So this might be one way of taking some measurements. Maybe not a calibrated tissue, but holding a tissue up in front of a return And people do this with bath fans too, just to see, is it getting any airflow? It's you don't know how much, but at least you know it's getting some. So we'll go through some troubleshooting that you can do to see where your problems might be. So take our DG700 and we'll use static pressure probes. And remember, the static pressure probe you want to be pointing into the airflow, and that gives us the static pressure we can think of as the bursting pressure, the outward pressure on the duct. What that pressure is. If you've got a straight tube or a straight hose pointing into the airflow, that's total pressure. That's measuring total pressure, and that's something different. That's related more to how much air is moving through it rather than what's the outward pressure on the duct. We want to be measuring static pressure, so we use our static pressure probe, and we're going to connect that up to channel A and turn on our DG700, and we're seeing a measurement at 8 pascals. I'm not sure how well you can read that, but we're measuring -8 pascals. So you can see I put the -8 here because maybe it's not showing up well enough on the gauge, but they're measuring -8 pascals. So what is that? What are we measuring? We're measuring, and we're assuming, I put the DG700 outside the house here so I could make it a little bigger, but actually when we're taking this measurement, we're going to be standing in the house here. So we're measuring the pressure in the duct with respect to the main body of the house. We're measuring the pressure across this return air grill here. So if you're measuring this from the crawl space, you'll need to run another tube up into the room. So we're measuring the room. We're measuring the pressure across this return air grill. And in this case, it's not a filter grill. We're putting a filter slot over here to take that measurement at that location. But so we're measuring the pressure across that return grill to see how restrictive that return grill is. And then now we're taking a measurement just before the filter in the return duct, and we're seeing a -28 at that location. So that -28 is the pressure difference between these two locations. So that's indicating, so we've got a pressure drop, right? We have to think of this as a pressure drop. We're getting more negative. The pressure's going down. And whenever we get a pressure drop, that's because we've got some restrictions in the airflow. And in this case, the airflow are a couple of elbows and a long length of duct is causing that drop in pressure. So the difference between those two is -20 pascals. So we've switched our tubing connections here now. So we're measuring the difference between the location just before the furnace filter and the pressure over on the side here. The difference between those two is 20 pascals. So we have a 20 pascal pressure drop along this section of return. The difference between -28 and 8, the distance between those two numbers is the change in pressure, which is -20. So now we know that we've got some restrictions based on elbows and length of duct. The next one, we're measuring the pressure on the other side of the filter, right before the air handler, or maybe we're measuring it right in the air handler cabinet, and we're getting a pressure here of -48. So we've got -48 on the other side of the filter. So then we'll change our hoses around. So So we've got, now we're measuring the static pressure across that furnace filter. And we're seeing a difference between those two of 20 pascals. So change in pressure, delta P, change in pressure of 20 pascals. So we've got another pressure drop across that filter. So we're seeing in this system, we're seeing the total pressure now, the pressure right before the fan on the return side is negative 48. So typical pressures across filters that you'll see anywhere from 20 to 100 pascals, depending on if it's a thin pleated filter or maybe it's a 3-inch wide or a 4-inch wide filter. With pleating is going to have less of a pressure drop. Dirty filters are going to cause higher pressures. Higher velocities are going to cause higher pressures. And a lot of times, when you buy filters, it'll show what a pressure drop is for a certain CFM. But if you have higher velocities, you're going to have higher pressures than what it's stating there. So you kind of need to know what your airflow is in order to know how much of a pressure drop that furnace filter is going to cause. So we've got the pressure across the filter is negative 20. So now we're measuring on the supply side. So now we're measuring the pressure. So now we're on the positive side. We're at plus 97. We're at plus 97. We're below the air conditioning coil. So this is the pressure on the supply side of the furnace. And then we'll connect up to that tube below. And now we're measuring the pressure across the fan. We're measuring the pressure across the furnace fan. So now we're seeing a positive pressure 97, negative pressure of 48. The difference between those is 145. So we've got a change in pressure of 145 pascals across the furnace fan. And that's referred to as an external static pressure. So when you hear of external static pressure measurements, in order to accurately take those measurements, you need 2 static pressure probes, and you can connect them to either side. We're in the pressure mode, so it doesn't matter which channel, but we want both those tubes connected to the same side. And that's measuring the difference between these two. So if you think of these pressures on a number line, we've got negative 48, and we need to go from negative 48 up to 0, and then from 0 to 97 to get the total difference between those two numbers on a number line. And that's what this 145 is. So we're taking the difference between these. So if you think of it arithmetically, we're taking 97 minus a negative 48, and minus a negative is the same as adding those two numbers together. So we're adding 97 and 48 and coming up with 145. So that's our external static pressure. And a lot of air handlers are, typical, you'll see 0.5 inches of water column, which is 125 pascals, or maybe 0.7 inches of water column. So that's the recommended external static pressure, total external static pressure for that given air handler. And if you go much higher than that, you're going to start affecting the life of that motor. You're going to shorten the life of that motor if you're running too high a static. So in this case, we've got 145 for a total. And it really should be 125 to be within the right range. So next in our troubleshooting process, we'll measure the pressure above the coil. So this way we can figure out how much resistance that coil is showing. And we're seeing now a positive 40. So we got positive 40 right above that coil, and now we'll hook up our tube, so we're measuring the pressure difference across that coil, and we're finding that to be negative 57. So we're seeing a 57 Pascal drop in pressure. And remember, a drop in pressure is indicating that that there's a restriction there. You know, when we measured our first pressure here, we saw a drop of pressure of 8 pascals across that filter. Well, this is the same. We've got a drop of pressure. We're going from our highest pressure down to our lowest pressure. So we're seeing negative 57 drop in pressure across that air conditioner coil. And you know, you'll see a range from 25 to 100. If you've got a block, you know, a really dirty coil, or if you've got a frozen coil, you may even see pressures higher than that. If you're seeing pressures of over 75 pascals, then it's time to really get in there. If there's not an access panel, you'll want to cut an access panel on the side of the duct and check it to see how dirty it is. It may be that that furnace filters haven't been changed often enough, and you know, when those coils have condensation on them when the air conditioner is running, they're going to collect a lot of dirt on them. So you're going to want to cut a hole in your duct and either remove that coil and clean it out, or do the best you can with it in place, and that may be your issue. Our next measurement we're taking up in the supply duct work, and we're seeing 20 pascals at that location. So we're seeing 20 pascals, so we have 40 pascals down here. So we've got a difference. We've dropped 20 pascals across that spot in the ductwork. So we're 20 pascals here. So now, if you took you know, measurement at one of these registers, you'd see that 20 Pascal drop from going from the ductwork down to this register. So you can see that all of these pressures are additive, and they'll be highest at the pressure right across the fan, and it's kind of counterintuitive, but the lower the pressures, the lower the external static pressure, the more that fan is going to be able to move. If you don't have any ductwork attached to it, there's going to be almost no, you know, very little change in pressure across that coil. And once we start adding all these restrictions, so on the supply side, this 97 is the additive restrictions of all of the ductwork, including the coil, everything on the supply side. And the highest pressure on the return side is going to be after the furnace filter, right closest to the, you know, closest to where the fan is. So and that's the additive of all of the return side. So this helps you, you know, wherever you see the biggest drop in pressure is the biggest issue, and you can look on your you know, the air conditioning coil, the installation instructions for that, the listing of that will show you what an expected drop across that coil will be, and you can kind of get an idea of what all of these additive things are. So, and you know, one other thing to keep in mind where it's important to take these measurements is if you're sealing ductwork, or you're recommending sealing ductwork, and you see that you have a 145 Pascal external static pressure before you start duct sealing, that pressure is only going to get higher as you seal those ducts, that external static pressure is going to get higher, because all of those leaks are providing pressure relief. And once you seal all those up, that pressure in the ducts are going to go up. So if you're going to seal those ducts, you're going to need to, or even recommend sealing those ducts. The issues with restrictive ductwork are going to need to be dealt with. And it's not necessarily up to you as a energy auditor or home performance technician to diagnose exactly what the solutions are, but make sure and make the homeowner and that contractor that's going to do the duct sealing aware that something needs to be done with the ductwork. So once the ducts are sealed, you won't have that issue of having too high a static pressure and too low of airflow. So when you think about it that way, intuitively, you would think that sealing the ducts, you'd be delivering more air to the room, and that's certainly true. You'll be delivering more of that air that you want delivered, but the total amount of air being delivered is going to be reduced. So the net maybe it won't change the airflow out of those registers as much as you think it will be. All the air that's being delivered is going where it's supposed to go, but there'll be less total airflow going through the system. So sealing the ducts may not necessarily solve your comfort problem if you've got really high static pressures that's reducing the total airflow through the system. Well, thanks for taking the time to attend our webinar today. This has been recorded, and we'll put it on our website soon. So if you wanna review it, look through it again, you can certainly do that, or have others in your company or others review it. And as we mentioned before, we're always looking for information on what types of webinars you haven't seen or you'd like to see in the future. Let us know if this was too complicated or not complicated enough. I mean, those are the kind of feedbacks we're looking for. If you'd like another webinar that will give more clarity on a certain area, something we covered, we can certainly do that too. So we'll take some time now to review the questions that we've had so far, and feel free to type in questions as you think of them. Maybe as some of the answers come up, it'll kind of spur your thinking, and you may have some additional questions. Go ahead and type those in, and we'll take some time to go over all of those questions now.
Okay, now we'll take some time to review the questions that have been asked so far, and you can feel free to continue typing in questions in the Q&A section at the right, and we'll try to get to all of those also. So some that were asked so far. When you're using the Duct Blaster fan to measure the air handler flow, which direction should the Duct Blaster fan face? And you want that to face into the air handler. So you want to be blowing additional air into the air handler to increase the flow going through the system. So you'll be pressurizing the system blowing into the return side when you're using the Duct Blaster fan to measure total air handler flow. And again, as I mentioned, if you have flow, let's say you only have a 2-ton system, you'll probably you're going to be trying to measure 800 CFM, so you'll need to have ring 1. You won't have the open fan under those conditions. So check if you know what your how many tons your system is, you can kind of approximate what your airflow is and put on rings appropriate to that amount of airflow you're trying to measure. Another question, can you use the flex duct for this method? So it's not uncommon to have a filter grill in the ceiling, and you're going to need to connect the duct blaster up to the ceiling. And you could tape that to some cardboard and tape some cardboard up there, or it does come with bungees, and maybe you could do that. But to be safe, you're probably going to want to use the flex duct with it, and you can certainly do that. It won't affect the accuracy, but the total amount of flow through the system will be reduced by about 15%. So you will get some reduction in total flow you can achieve, but it won't affect the accuracy of your readings. Another question, when you're doing that test, do you run the air handler fan? And the answer is yes. You will want to be running the air handler fan during that test, and you'll see flow on your DG700 once you turn that air handler on, because there's flow going through the fan, and then you'll want to increase that flow until you get to the what the static was for the normal system operating pressures. What speed should the air handler be running on? If you're doing a test for air conditioning, you'll have the thermostat set for air conditioning, and you'll turn it on for that mode, and you'll have there's so many CFM per ton that you want to achieve for air conditioning, and for heat there's so many CFM per 100,000 or per 1,000 BTUs of output. So you'll want that set properly for heating also. So depending on what you're trying to learn, maybe you want to test it both ways, and test your airflow both ways, or test your static pressures both ways, depending on what you're trying to learn. Let's see. Let's see, Tom had a question about the DG700 to Duct Blaster hookup for measuring the normal system operating pressure. You'll set it up just like you would for a Duct Blaster test, but you'll be measuring, instead of measuring channel A in a supply register, you'll be measuring it right in the plenum. So you'll be above the air conditioner coil in the supply plenum. And then, as always, channel B will be going to the duct blaster fan. The input on channel B, the upper right tap, will be going to your duct blaster fan. And Scott says, does temperature, cold or hot, affect the static pressure? It should not. Those temperature adjustments we were talking about is related to flow. So that's you're adjusting the flow measurement that's being displayed on the DG700, and not static pressure. So you wouldn't need to adjust the static pressure measurements. Well, thanks for attending the webinar, and thanks for asking questions. And feel free to email or call me if you have any additional questions, or if you have any suggestions for what you'd like to see in future webinars. Thanks.